Let's look at an example where we're going to draw the shear force diagram and the bending moment diagram. This particular problem is the same problem that we've seen in a prior video, and where we calculated the internal forces at C. In that prior video, we already calculated the reaction forces, and that's what you see in the right hand side of the screen right now. That is the free body diagram, and in that free body diagram we were able to find reaction forces. AY is 1.7714 kilonewtons and dy is 4.286 kilonewtons. I'm keeping those four significant figures as I consider those intermediate calculations to be able to find the final answer, which is our equations of shear force and bending moment diagrams. So forgot something here. This distance over here is also 2 meters. All right. So if you have questions about those reaction forces, I encourage you to go back and look at the video where we calculate what is an example about internal forces at a point. So those forces come from that video. Now in this video, we're going to be looking at the shear force diagrams and the bending moment diagrams. And in that particular case, what we need to do is make cuts as the loading condition changes through the beam. So my first cut is going to be between 0 and 3 meters. So somewhere over here. Going to be the cut somewhere over there. All right. And I'm going to draw a free body diagram for that cut. Then we're going to do some equations of equilibrium. And with those equations of equilibrium, we should be able to find the equations. Now they're going to be equations as a function of x that describe my shear force and my bending moment. So let's start with that part. So now we can say that for x between 0 and 3 meters, right? That's the key. And we need to chunk this in two parts, one between 0 and 3, and the other one between 3 and 7 meters. Right, for x between 0 and 3, I'm going to start doing my free body diagram. Let me turn the camera off so we can have a little bit more space. The free body diagram, I'm going to choose the left-hand side, but it is also possible to choose the right-hand side of the free body diagram. The solution should be exactly the same. All right, in my left-hand side of that free body diagram, I'm going to see A. So over here is A. I'm going to see a little bit of the beam. I'm going to see my reaction forces. So I'm going to have AY 1.714 kilonewtons. I'm going to see my AX, that's 0. I'm going to put it here. So we know that we have calculated before. And the other thing I'm going to see is going to be my internal forces. So my internal forces are going to be my shear. Now this is a function of x. My moment, function of x. And my normal force, which is a function of x as well. All right, what else do I need in this free body diagram? I need my axis. So my x-axis is going to be this direction. Y-axis is going to be this direction. And I need to find some distance between A and my cut. And since we're trying to find those equations as a function of x, we're going to find out is that that distance is actually x, right? That I'm going to define that as x. That's my x-axis anyway, so that's going to be described by that variable x. All right, let's write the equations of equilibrium. So for those equations of equilibrium, I'm going to start, let's start with the easy one. Some of the forces in x should be equal to 0. The only forces that we have in x are my AX, which is 0, and my normal force, which is unknown. So my normal force as a function of x is equal to 0. What that means is that normal force is 0 for any values of x between 0 and 3. All right, let's do my next equation of equilibrium. I'm going to do, let's do some of the forces in y. Why not? All right, forces in y, I have my AY, right? That's going up, so that is 1.714 kilonewtons. And the only other force is going to be my shear force. That's going down, so it's going to be negative V of x. From this, we can find my shear force, and my shear force is a function of x, is going to be equal to 1.71 kilonewtons. I'm going to leave it in 3 significant figures, since this is going to be one of the answers that I'm looking for. Now remember, this is, right, for x between 0 and 3. Just as a reminder, I'm going to write it right next to it, just to make sure that we understand this for any values of x between 0 and 3. Finally, I'm going to do some of the moments. I'm going to do some of the moments about the cut, so about this point over here. Reason why I want to use that is my shear force does not produce any moments. It's a little bit easier to do the equations that way. But it is possible to do the same by taking moments about any other point on that beam. All right, so my forces, my moments are going to be m of x, that's positive, as thrown in there. And my shear force creates no moment about the cut, but my AY does create a moment about the cut. That's going to be a negative moment, and that's going to be negative 1.714 times x. 1.714, that's the force, and x is the distance, the perpendicular distance to the line of action of the force. From here we can find that my moment as a function of x is going to be equal to 1.71 x to keep my significant figures to 3, and this is going to be kilonewtons meter. That's going to be part of my answer as well. Now this is for, again, x between 0 and 3 meters. 0 and 3 meters. All right, so that is describing my normal force, my shear force, and my bending moment between 0 and 3. Now what I need to do is repeat the process by now doing a cut between B and D, right? That's the next set of length of that beam that is going to have a different type of loading, and we need to analyze it. So let's make a second cut. Let's do it green, why not? It's going to be somewhere from x between 3 and 7. And that's going to be our next set of equations. All right, so for x between 3 meters and 7 meters, that's what we're looking for. And my free body diagram is going to include now part of that distributed force, right? So I'm going to draw my first part that does not have any loading, and I need to write something that is that has the distributed force, but is anywhere between B and D on that top diagram. All right, so my left-hand side, I'm going to have A. This is my A in here. I have my AX equal to 0. My AY we already calculated as 1.714 kilonewtons. When I have my 3 meters that are not loaded, and they're going to have a portion of the beam that is loaded, right? So this part over here is going to be loaded with this 1.5 kilonewtons over meter force. What else do I see? I see my internal forces. That's going to be my shear force. Remember, shear force, we define it by definition. We need to draw it down. And now this is a function of x. My normal force, also a function of x. And my bending moment, also a function of x. So those are the three unknowns that we're going to try to find. We name our axis. Here's my x-axis. This is my y-axis for my free body diagram. And the other thing I need is some distances. Okay, so let's look at these distances carefully. This distance between A and the cut, that's going to be x, right? It's a variable. So that means, since this distance over here is 3 meters, that means that this distance that is going to be loaded, this part over here, that is going to be x minus 3, right? X is the whole thing. At the beginning we have those 3 meters. That means that the remaining is that x minus 3. Very good. I think we have all the information that we need. Now what we need to do, since we need to simplify that distributed load with something else, we need to do an equivalent diagram that considers the equivalent point load, or the point load that has the same external influence on that beam that distributed load. So my equivalent system is going to be something like this. I'm going to have to redraw most of it, but that's okay. This is part of the analysis. I do strongly encourage you to do these diagrams. Don't try to do all of these diagrams by memory or anything like that, because we're going to miss something when we try to do that. Right, and here I have my reaction force. This is 1.714 kilonewtons. This is going to be AX equal to 0. We're going to have, now that the distributed load, remember we can replace that by a point load going through the centroid of that area, right? So that centroid of that area is going to be somewhere in here, is the middle of that rectangle, that distributed load. And we also have our external forces, or sorry, our internal forces. Let me change that to red. Those are the unknowns. We have V as a function of x. Normal force is a function of x. M as a function of x. All right, so now we need to define the magnitude of that equivalent point load. And we need to define the location of that magnitude of that equivalent point load. The magnitude is defined by the area on that distributed force. The height as drawn there is 1.5 kilonewtons over a meter, and the width is x minus 3. So this is a rectangle. So what the magnitude of that is going to be 1.5 times x minus 3, right? Width times height. What this is allowing us to do is look at the equation. As x increases, the amount of loading that is being applied to that beam is increasing as well, which makes complete sense, right? As we have a bigger chunk of that beam, we're going to have a bigger chunk of that distributed load. Now, we also need to find the location of that. In the diagram above, we see that the width is x minus 3, and for a rectangle, we know that the centroid is right in the middle, which means that this distance between the equivalent point load and my cut, that distance, is going to be x minus 3 over 2, right? Because it's right in the middle. And we also know that the distance from this end to the cut is going to be x. So I think this is going to be the diagram that we can use now to do our equations of equilibrium. All right, let's do our equations of equilibrium. and see how it goes. I'm going to go back and write equations of equilibrium here on the top, because it's going to be a little bit the long side, and I want to make sure that everything fits in the in one page. All right, equations of equilibrium. Let's go back to the diagram at the bottom. We can do some of the forces in x. That's going to be the easiest one, right? Sum of the forces in x equal to 0. The only thing that we have in x is ax, which is 0, and n of x. So n of x is going to be equal to 0. By the way, that is not always the case, okay? That is not always the case. So don't make the assumption that your normal force is always going to be 0. All right, let's do some of the forces in y. Let's see what we get in there. Let's see what forces we have in that diagram at the bottom. We have that 1.714 kilonewtons. So 1.714 kilonewtons positive. Now we have the equivalent point load. That's going to be going down, so negative. And that will be 1.5 times x minus 3. We also have our shear force, so this is going to be our V of x. From here, we can solve for our shear force, and our shear force is going to be V of x is going to be equal to 1.714. Let's see, multiply this will be plus 4.5. That will be that 1.5 times 3. And then we have minus 1.5x, right? So I just solve for V of x from that equation on top. When I write this a little bit more compact, I'm gonna combine the 1.714 with that 4.5. We have this is equal to 6.21 minus 1.5x kilonewtons. Again, trying to keep our 3 significant figures in our final answers, and remembering to put the our units of kilonewtons in this case. This equation over here is also, we need to make sure that we remember that this is between 3 and 7 meters, right? 3 meters and 7 meters, just to make sure that we have that clear. Now, finally, what we're going to have is the sum of the moments by the cut. That's going to be equal to 0. And what we're going to do is we're going to say is, let's say at the cut we have that moment, m of x. We have the load on the left-hand side, that 1.714 kilonewtons. The perpendicular distance to that is x, as we can see at the bottom of that diagram, right? And that will create a negative moment, so minus 1.714x. And now we have that equivalent point load, that 1.5 times x minus 3. That's going to create a positive moment. The magnitude of that force is 1.5 times x minus 3. My perpendicular distance is going to be x minus 3 over 2. Right? All right, so we need to do a little bit of algebra in here to solve for this m of x. So my m of x is going to be, let's see, that will become positive when we put in the other side of the equal. So 1.714x minus, I'm going to take that 1.5 and that 2 out of there. And then I have this x minus 3 times x minus 3. That gives me x squared minus 6x plus 9. This is just algebra. There's nothing magical in here. And if I simplify this, we get m of x is going to be equal to, let's see, 1.714x minus, that would be 0.75x square plus 4.5x minus 6.75. Now the m of x, we keep simplifying this, we have minus 0.75x squared plus 6.21x minus 6.75, and the units will be kilonewtons times meter. Good. This is great. So we now have the equations that describe that shear force, and we have the equation that describe the bending moment for the whole beam, right? This is the main thing that I want you to learn in statics. There are going to be some other things you're going to learn later on in other courses that are going to allow you to do more with these bending moment diagrams and these shear force diagrams. Now, I'm going to end the video here. I'm going to create an additional video where we're going to look at how do we plot these equations into some axes, and also how are we going to kind of describe some key points of these shear and bending moment diagrams.